chemistry book, and we're in chapter 17, section 4 now, the effects of radiation on matter. So how does radiation affect things? How does it affect people? How does it affect the earth? What does radiation do? So the problem, as particles of radiation careen through matter, they may collide with electrons with such force that electrons are knocked loose from their parent atoms, forming ions. For this reason, alpha rays, beta rays, gamma rays, X-rays, and neutrons are all ionizing radiation. And this is defined as a radiation capable of causing ionization. So basically the radiation, what it's saying here, when radiation causes ionization, which causes a splitting of ions into ions, so you have positive and negative, as positive and negative electrons or protons of those charges. And this is what actually can harm, the molecules that are struck by the ionizing radiation, and they break apart due to the ionization. So the problem is ionization of radiation, okay? So you know that. So neutrons cause ionization too, but indirectly by reacting with target nuclei, and they form alpha and beta and gamma. So even though neutron rays are neutral, they also can cause different reactions to happen as the neutron crashes into the nucleus or whatever, and they produce gamma rays and alpha rays and beta rays, and so they can cause ionization too. So all radiation can be potentially harmful, is what they're saying. So it basically, how does this look, in living cells? With ionization in living cells, with ionization, we're exposed to radiation, and this can damage our cells' molecular machinery. And it also can cause changes in our DNA. So it's very important as for being shielded from large doses of radiation. So cells that are most susceptible to radiation damage are when they are dividing. And so when a cell is dividing, tissues that don't divide much, like brain cells and muscle cells, do not divide as much, so they're less susceptible to radiation. But those cells that are going from the bone marrow and the GI tract, they divide a lot, and so those cells would be more susceptible to damage. So, in fact, that's why they usually use radiation treatment for cancer, because cancer cells are dividing really, really quickly. So when they bring the radiation cell to the dividing cells of cancer cells, are killed by the radiation because they're the ones that are dividing the most, when cells divide. So let's go on from there. So looking about protection from the different radiations. So let's look up here. Various types of radiation differ in their effects on the body. So as for exposed to external source of alpha radiation, such as dust contaminated with alpha-emitting isotope, a person would experience little effect because alpha particles are unable to penetrate the skin. So alpha particles, radiation, will not go through your skin. So most likely, being through alpha radiation is not going to necessarily hurt yourself. But beta radiation can give you moderate to severe skin burns. So beta reactions, you should put on suitable clothing, and then that will keep the radiation from the beta from hitting you, the radiation burns prevented by clothing. But gamma rays and X-rays and neutron rays pass through the surfaces and pass through the area of your skin, and so they can actually hurt you in that midst if you don't have some type of barrier to protect you. So, but it says alpha and beta emitters become far more dangerous if they're ingested or inhaled. So if you had if you were inhaling alpha or beta emitter, that you would be, your body would be drastically, in danger of being compromised, right? And so, but as for the gamma radiation, X-rays and neutrons can pass right through the body's surface and tend to produce whole body effects rather than localized burns. So how do we detect radiation? So they have different ways of detecting. So there's some of them are, the detectors are small gas-filled chambers that detect ionization. They're looking for ionization because that detects what radiation will look like. And some are fluorescent liquid or crystals that detect it. And some are semiconductor computer chips, type semiconductor chips that they have to be able to detect radiation. And some measure the energy of radiation to determine the density. So here we have, here's an ion chamber radiation meter. So that's why a lot of people that are thinking they're exposed to radiation of, nuclear radiation, that they have these meters on them or something that can tell if the radiation, how much radiation. And here's a personal dosimeter that tells how much radiation, detecting radiation. So it's pretty easy to detect if you have one of these meters, and they have them very commonly. Measuring radiation. So let's go on to measuring radiation. So up here is units of radiation measurement. So radiation units are measured in rad, R-A-D, or REM. The difference is rads will tell the absorbed dose rad measurement, and the REM are used for biological dose equivalents. So if you're looking for in a human living being, you'd use the REM. There's also the sievert, SV is another. So let's just look. RAD, radiation absorbed dose, equal to the absorption of 0.01 joule of radiation per kilogram of mass. And then the gray is another method for absorbed dose. And this is a newer, GY it's called, equal to the absorption of 1 joule of radiation per kilogram of mass. So 1 GY equals 100 rads. And this is REM, amount of radiation that will cause the same amount of biological injury as a rad, or X-rays or gamma. So REM is measuring the biological injury, which means basically how it's affecting a living person, living being. And sievert, the amount of radiation that will cause the same amount of biological injury as 1 GI of X-rays or gamma. Only this. So this is basically replacing this and this. So it depends. But these are not used as, these are SI units now, although they're not used as much as rad and REM still are being used. Okay. So these are the measuring. Let's go on to the next. Health effects of radiation. So health effects. We know that radiation can be detrimental to our health, right? So how? The average American receives 300 to 400 millirem of radiation per year, mostly from natural sources, but we are exposed to this radiation. And this vastly increased exposures, if you increase this 300 to 400 millirem to 10,000 to 50,000 millirem, and this would cause temporary effects such as change in our blood cell counts, aplastic anemia, and then radiation sickness, which is the top if you were really exposed to high doses of radiation. And it can occur at exposures of 200 to 300 rem, not millirem, but rem. And exposure of 400 rem will cause severe radiation and a 50% of chance of cancer. So when you are exposed to high radiation, you definitely can be exposed to getting cancer in your lifetime. So radiation can cause cancer. Whole body exposures of 600 rem, that's a lot, are usually fatal within 30 days. Say you had a nuclear, you're in a nuclear reactor or something, or a nuclear bomb or something, you could basically die within 30 days if you're not already. So that's just telling you the effects of radiation. It also says, interestingly, far larger doses can be tolerated if the radiation is received gradually rather than all at once. So if you're gradually receiving like 130 MRM right here, REMs for 50 years, that this would be a cumulative dose of 2.4 million, but you'd be unlikely to suffer radiation sickness or severe symptoms because it was very gradual. So, sources of radiation exposure, it says that everyone is exposed to radiation on the planet Earth. And so it's a common misconception that exposure to nuclear radiation is somehow artificial as a result of our technology. Actually, the Earth is pretty radioactive, huh? So it's a radioactive planet, and we're constantly exposed to natural nuclear radiation. So let's look at the table here, see? So here we have natural sources of radiation. Radon gas is emitted by the Earth. This is our average dose per year, and the percentage is 54% of the total. Cosmic rays and solar flares give radiation, of course, and that's 7%. And so the dose per year. The ground, there's radioactivity minerals and such in the ground. We can be exposed to 7% in the ground. And just in the human body, even in another person's human body, you can have some radiation exposure, 7%. Then we have artificial sources of radiation, such as medical procedures we go through, certain medical, if we have ultrasound, if we have x-rays and all these different things, medical procedures are 22%. So we have x-rays of our teeth, we have x-rays of our body, we have all different kinds of medical procedures that we go through that can produce radiation, so. On to consumer products, building materials, certain building materials, 3% of building materials can give us radiation. TV computer screens give us radiation, 0.3%. Nuclear power, 0.003%. Anyway, total exposure is 100%, and you can see what we're exposed to. It says here, U.S. average exposure is higher for people living in energy-efficient homes due to more air recirculation. I didn't know that. And in areas with rocky soils, as in New England or Rocky Mountain states, produce more radiation. I didn't know that either. For someone living at sea level, radiation exposure increases with altitude. So if you go up further, higher radiation, you're flying 1,000 miles on a jet plane, as when you're flying more, adds more radiation to you. Didn't know that. So from naturally occurring radioactive isotopes, potassium, carbon in the body. For each X-ray, it involves 0.1 millirem of exposure. Each chest X-ray, each skull X-ray, each CAT scan of the brain, each ultrasound too, each X-ray of the lower digestive tract, goes on to CAT scans of the abdomen. All these produce radiation. Okay. So when we talk about radiation, then you can see how it has an effect on us. So it says here, I like this. Fortunately, God has designed the human body with the ability to easily repair limited radiation damage, so that lower level exposure has never been shown to cause any harmful effects. So if there's lower level, we're going to be okay, right? Though nowadays you want to wear sunscreen for radiation from electromagnetic radiation and gamma rays and ultraviolet rays and all that too. So, but anyway, you can see how, but radiation from nuclear is still we still basically are receiving radiation from all of these different areas. So let's do the section review and then we'll finish up this section. Go on, we have one more section to do, which is kind of a long section. So why are neutrons considered ionizing radiation even though they cannot directly cause ionization? So neutrons, basically neutron rays are bombarding other atoms, and when they hit the nucleus, they'll bombard them and produce gamma rays and cause alpha and beta to come from the neutrons as they hit others. So basically they don't in themselves, they're neutral, they're not ions, but they cause, because what we're concerned about, of course, is ionizing radiation, that is the radiation that will cause problems. Why are cells of the gastrointestinal tract, bone marrow, more susceptible to radiation damage than brain or muscle cells? Because radiation likes to attack those cells that are dividing quickly. As they're quickly dividing, it basically attacks them in the DNA of those cells. And gastrointestinal and intestinal and bone marrow, they are fast dividing, so they'll be attacked before. And that's also why radiation is used for cancer, because cancer cells divide very quickly, so they'll be attacked first. Number 3, why would different precautions be required when handling alpha or beta emitters than when handling gamma emitters? So why would precautions? Okay, so alpha and beta protectors are protected by our skin, right? Alpha and beta radiation do not go through our skin much. A little bit beta may give us a little sunburn or whatever, but when we're handling gamma emitters, we basically have to put on over lead. They have to put lead on you, or they have to cover with concrete if it's a nuclear reactor. So that's why, because alpha and beta don't go through our skin. So how is a nuclear radiation detected? So they have those monitors, those little monitors that are made different ones. Some small glass filled so they can detect ionization. Some fluorescent liquids and some semiconductive chips, and dosimeters, ion chambers and dosimeters are all different types of meters to measure the amount of radiation we receive. What units are used to measure radiation exposure? The rad and the ram. Remember up there here? I think it's right up here. Okay. No, it's not. It was on the last page here. Let's go back. Right here, the rad and the ram. The ram's used for biological. Okay. Let's go back. Those are the units that we went over. Which units take into account the differing effects of radiation on living things? The REM, R-E-M, or the sievert, but the REM. Okay, the 3 Mile Island nuclear accident in 1979 exposed the surrounding population to an average radiation dose of 1.2 millirems, or megarems, or millirems, I'm sorry. Knowing what you know about natural background of radiation, do you think this would be harmful? Okay, so when we look at that, I would say 1.2 is not going to be harmful. In fact, 3 Mile Island nuclear accident, no one was hurt and no one was drastically exposed to radiation in that one, but the radiation dose was 1.2. So if we looked up here, 1.2 is going to be would be very, very strong in millirem. The average American receives 300 to 400 millirems a year, so it would not, as you see the amount as a dosimeter or whatever takes would be not. The average adult receiving 300 to 400 millirems per year, so this would run not a large amount, so we wouldn't have to really be concerned in that situation. Now, some nuclear accidents, especially Chernobyl, you would have to be concerned. So anyway, that is the end of this section, and then we'll go on with section 5, and we'll be finished with this chapter on nuclear science.